Survey of Calculus, Chapter 6, Section 2, Partial Derivatives. Let's say we have a function in multiple variables, like 2 or 3 variables. If we were to fix the values of all the variables but one, in other words, instead of being variable, they actually had a value, then we could easily take the derivative. For example, let's say we have a function that's using x and y. You see it here, x squared y cubed plus xy plus 4y squared. Let's say that we define y as being 3. So we would put 3 in for y. And that would give us 27x squared plus 3x plus 36. Well, now we've only got one variable, and taking the derivative of it with respect to x would be very easy. It would just be 54x plus 3. So instead of actually assigning a value to y, instead what we're going to do is we're going to kind of mentally consider it fixed. We're going to pretend it's a constant, and then we're going to take the derivative of the function with respect to x. And when we do that, it's called taking the partial derivative of f with respect to x, and it's symbolized by delta f over delta x. Now you might be thinking, well, I thought delta was a triangle. Capital delta, Greek has capital and lowercase letters, just like our language does, just like English does. The triangle is the capital letter delta. This kind of, if you look at it, it kind of looks like a D that melted. You know, it's kind of squiggly D there. That's the lowercase delta. Okay, so this lowercase delta, instead of an English D, it's going to use the Greek letter, and this is called a partial derivative. Whatever we're taking the partial derivative with respect to, that's going to be the one thing that's considered a variable. Everything else is going to be considered a constant. We can find the partial derivative of each variable of the function using this method. So what you can do is you can go through and find the partial derivative with respect to x, and then you can go back and find the partial derivative with respect to y and z, and for however many variables you have. The next slide is going to give us the formal definition of partial derivatives, but I don't want you to get freaked out by that. You don't necessarily need to worry about it. It involves limits and all sorts of stuff. I'm going to show it to you, but I don't want you to obsess on it. Just want to show it to you because it is the formal definition. But we're going to do what we just talked about as far as procedure goes. Formal definition looks like, and again, like I said, it's got limits there and it looks really confusing. But in essence, it's really just what I talked about. It's just what I talked about a second ago. That's how we're going to do it. Now, we often write f sub x of xy or f sub x for the partial derivative of f with respect to x. So this is another notation thing here. We had the delta. We also have this notation. F sub y would be the partial derivative of f with respect to y. If there was if z equals f of xy, then we could do z sub x for the partial derivative with respect to x and z sub y. If the function was defined as being equal to another variable z, then you could use that for the notation as well. Okay, so let's try this out. W is the name of the function, so notice that all of what we're finding, it's delta w over delta something else. We're going to find the partial derivative of w with respect to x, with respect to y, and with respect to z. Now, here's the tricky part, guys. You have to remember that the other variables are constant. You have to treat them as a constant, and that gets a little tricky. It gets a little mind-blowing. So I want you to give this a try, but remember, the first thing you're going to do is you're going to consider x is your only variable. So y is a constant and z is a constant. Okay? And think about how you take the derivatives of constants when the variable is not attached. Just pause the recording, give this a try, resume, and check your answer, and we'll talk through how to do this. Okay, so we're going to regard x as the variable, y and z as the constants. Now, what that gives us, the first x squared becomes 2x. And then we have minus xy. Well, that would be just minus y, because if it was like minus 2x, it would just be minus 2. So since y is considered a constant, minus xy is going to be just minus y. The y squared, that's a constant, it goes away. 2yz goes away. 2z squared, 0, z, 0. All the rest is just constants with no variables. So they all disappear, and we're just left with 2x minus y. Now, if you think that maybe you've got it now and you want to try it again for doing the derivative with respect to y, the partial derivative, you might want to pause and give that a try. So if you want to do that, go ahead and pause now. And if not, we're just going to move on and do the next one. So here's our equation again, just so we don't have to switch back and forth. And taking the partial derivative with respect to y, we get negative x plus 2y plus 2z. Now here's y. X squared, again, everything but y is a constant. So x squared is a constant, it goes away. Minus xy. Well, you're just left with the constant, which is minus x. Y squared becomes 2y. 2yz becomes 2z because, again, 2 and z are constants. And then 2z squared and plus z are both constants, and they don't have variables attached. They don't have a y attached, so they go away and become 0. So we're left with negative x plus 2y plus 2z. Now let's do z. The x squared goes away. The xy goes away. The y squared goes away. We only have to deal with things that have z's inside. In fact, that might be a good way to think about it. If the term doesn't have the variable you're taking the partial derivative with respect to, it's going to become 0. So you can completely ignore those. So we just have 2y plus 4z plus 1. All right, now try this one. And again, this notation, what it means is you're going to take the partial derivative with respect to x and the partial derivative with respect to y. Go ahead and give that a try. Pause the recording and then resume to check your answer. So, with respect to x, again, we're treating y as a constant. So you don't need to do the multiplication property. It's just 6xy. And then xy becomes just y. The variable drops out. And then treating x and x squared as constants, we have 3x squared plus x. Okay, here's another one to try. Find the partial derivative with respect to x and the partial derivative with respect to y. Okay, for x, we have 21x squared, y squared. So the x, the 3 comes down front, gets multiplied by the 7, that's 21. The power goes down by 1, x squared. Y squared is a constant that's attached, so we just leave it. X over y is like 1 over y times x. So it just leaves us with 1 over y. And then going back and taking care of the y, again, treat x as the constant. So the y squared, the 2 comes in front and becomes 14x to the third y. And then the x over y would be like x times y to the minus 1. So it would be the minus 1 would come down front and make it a plus, and you'd have x y to the minus 2, or x over y squared. All right, now we've got some logarithms and e's involved, but don't let those freak you out. Just be calm. Remember, the derivative of e to the x is e to the x. If it's a derivative of e to the x times something, then you're going to do e to the x times the derivative of that. And the natural log, the derivative of the natural log of x is 1 over x. So pause the recording, give this a try, and resume to check your answer. All right, so for e to the xy, the derivative of e to the xy is e to the xy times the derivative of xy, which would be y, plus, again, y is your constant. The derivative of natural log of x is 1 over x. So we have y e to the xy plus y over x. And for the partial derivative with respect to y, it's very similar. It's going to be e to the xy times the derivative of xy. This time that derivative is going to be x. And then remember, x is a constant here, so the y becomes 1. It's just plus 1 times the natural log of x, because that's going to be a constant. All All right, let's try an example. A cell phone company has the following production function for a certain product. Okay. P is the number of units produced, X is the units of labor, and Y is the units of capital. Find the number of units produced with 125 labor and 64 capital. Okay, for part A, all you're going to do is put in 125 for X and 64 for Y, put it in your calculator and get an answer. That's all you're going to do for A. For B, the marginal productivities. What that means is you're going to take the partial derivative with respect to X, and that will give you the marginal labor. And then you're going to do the same thing with respect to Y, and that will give you the marginal for capital. Okay, pause the recording, give these a try, resume to check your answer. And once you're done, evaluate the marginal productivities at X equals 125 and 64. After you've found B, put in 125 for X, and put in 64 for Y and get actual number answers. Sorry, I delayed that. Pause the recording, and if you need to finish that up, do that, and then resume to check your answer. Okay, so the first thing, like I said, all you're doing is putting the numbers into the original equation, and you're going to get 5,000 units. The marginal productivity was taking the partial derivative with respect to X for labor. And when we do that, we get 100 y to the 1/3 over 3 y to the x to the 1/3. Now, again, you could have left that 100 over 3 x to the negative 1/3 y to the 1/3. That's fine. And then for capital, we get 50 x to the 2/3 over 3 y to the 2/3. Or you could have left it 50/3 x to the 2/3 y to the negative 2/3. And then putting in 125 and 64 for those. Let's see, we get 26 and 2/3 for labor. And for capital, we get 26 and 1/24. All right, so this is just kind of a definition here. Second order partial derivatives. Second order derivative is when you take the derivative of a derivative, which normally is not that big a deal. We've done that before. For partial derivatives, it's a little more involved. It's not necessarily more complicated. What you're going to do is you're going to take the partial derivative of the variables first, and then what you're going to do is, let's say and you're going to only be dealing with two variables, thankfully, because that'll make it a lot easier. What you're going to do is you're going to take the partial derivative with respect to X and the partial derivative with respect to Y, and those will be your first order. For the second, you take the partial derivative with respect to X, and you take its partial derivative with respect to X. And then you also take its derivative with respect to Y. So each first partial derivative is going to produce 2 seconds. Okay, so you're going to do the partial derivative with respect to X, and then take the partial derivative of that with respect to X. You're going to take the partial derivative with respect to X and take the partial derivative of that with respect to Y. And then you're going to do the partial derivative with respect to Y, and then take the derivative of that with respect to X, take the partial derivative with respect to Y, and take the partial derivative of that with respect to Y. So a two-variable equation is going to generate two partial first derivatives for second-order derivatives. Okay? It's not really complicated. It's not any more complicated than just doing the first. It's just more work, and it's easy to make careless mistakes. Believe me, I practiced these, I know. It's really easy to get a little confused and make careless mistakes. So you got to really be careful and organize your work. All right, so let's try finding the second order partial derivatives for this. Pause the recording, give it a try, and resume to check your answer. It's going to show the first derivatives, and then we'll pause again after that. So if you want to wait and check that. Okay, so the first derivative with respect to X, you're going to get 2xy to the third plus 4x to the third y plus e to the y. And then taking the derivative of that with respect to x gives you 2y to the third plus 12x squared y. Again, first derivative with respect to x is 2xy to the third plus 4x to the third y plus e to the y. Same thing we got before, but now we're going to take the derivative of that with respect to y. So, in other words, x is going to be considered your constant. And that's going to look like 6xy squared plus 4x to the third plus e to the y. Now we're going to do the partial derivative of y and do the 2 that come off of that. Okay, so the partial derivative with respect to y is 3x squared y squared plus x to the fourth plus x e to the y. Now take the derivative of that partial derivative with respect to x. You get 6xy squared plus 4x to the third plus e to the y. And now we're going to do f sub yy. So again, here's the first derivative, partial derivative with respect to y. Taking the derivative of that, the partial derivative with respect to y, we get 6x squared y plus x e to the y. All right, now here's another one. Give it a try. Remember what I said. What I would do is I would do the partial derivative with respect to x, the partial derivative with respect to y. I'd get those done first, and then I would take and do the 2 off of each of those second. Keep it very organized and keep in the front of your mind what is the variable and what is the constant. Pause the recording, give this a try, and resume to check your answer. Okay, if you want to pause here and kind of look over these and make sure you've got it and you understand it, look back at what you did. If you made a mistake, see if you can find it. Go ahead and do that. Otherwise, we will keep going. Okay, this is just a summary of the section. Again, you've got the formal definition there. Don't worry about the formal definition. Just worry about the procedure we talked about. That's the most important part. And there's the notation also. And then we talked about second order derivatives. And notice they say often but not always f sub xy equals f sub yx. You might look back at some of the ones we do and see if they did or didn't. Notice again it says often but not always, so it doesn't have to be equal. Okay, the rest of this is just some practice. By the way, that notation there, what it means is you're going to take those partial derivatives, and then when you get them, you're going to put in -2 for x and -3 for y. And then the second one, you're going to put in 0 for x and -5 for y. All right, so pause the recording as you go through these and give them a try. Resume to check your answer.